Hi there. I'd like to spend a few minutes now, hopefully just a few minutes, kind of reviewing some of the important underlying concepts and ideas that help to define the skills and knowledge that you are going to be expected to demonstrate on the upcoming midterm. And because the midterm covers all the course objectives, I think something like this is really kind of necessary. Also, it'll give you one more chance to sort of dive into the notes that are going to be the foundation of the items that are measured, and I want to talk a little bit about that. So let's just get started. I'm going to go kind of fast because I really want this to be not so long. So I'm going to start here on the course website, and I wanted just to remind you the most important thing about the upcoming exam is the fact that it measures all of the objectives listed for the course that are not italicized. And so if there are italicized objectives, information about those are provided in the notes, but there won't be any items on the upcoming midterm that measure those. So that's really important. Now, the other thing I want to say about the website is that we have, for example, I'm going to go to part 3, the information and practice, and I just wanted to remind you that at the bottom of the information and practice pages for each of the 4 parts of the class, there is a file. Some of them are embedded and some of them are documents. And these documents provide practice over the skills that are going to be measured on the exam. And the items are going to be very similar to the items that are included in the practice. And hopefully you had a chance to go through those practice items and you saw how they were aligned specifically to the numbered objectives that are going to be measured on the course. So that's really an important thing to make sure that you do. If you, for some reason, didn't go through the practice items, please do yourself a favor and make sure that you go through those and practice, and contact me if there's something you don't understand before the upcoming exam. Okay, so with that in mind, let me walk through some of the course notes that align directly with the skills to be measured, and also provides me with an opportunity to elaborate a little bit on some of the ideas and concepts, because I really I didn't have a chance to do this in my more typical lecture format, and I thought it might help you review for the exam. So here I am in the course notes file. This is the foundational kind of depository of the information and examples that are going to be addressed on the midterm. And I just wanted to go through, again, not all of the objectives, but just some of them, and some of the important ideas, and I'm going to go kind of fast. So here I am at the very beginning of part 1, and you'll notice that I have some information that supports the italicized objectives, and I think it's really important, but this information is not going to be addressed on the exam. The first item, the first objective that is going to be measured is 1.3, which is describe how science represents a way of knowing, and differentiate between science and other ways of knowing. And I provide some information about this, but I just wanted to stop for a minute and elaborate on why this is important, because the best thing that you can learn in this class is how to think more scientifically and how to embrace the scientific way of knowing. Because as professionals, you're going to be presented with a lot of ideas about your practice that may not have any roots in scientific support. And so a good example of this would be if you're a reading teacher and you're adopting materials or approaches to helping people learn how to read that may or may not be grounded in any kind of research or any kind of observations, careful observations that resulted in better ways, more effective ways of doing things that would support what you think is important for your students to learn. I was a science teacher for a number of years, and I embraced an approach to teaching science that was grounded in a really good body of literature. It's called the learning cycle approach, and it was grounded in literature that demonstrated scientifically that students learned how to think more scientifically through that approach. And because that was my primary goal or mission with any of my classes, regardless of the content, is that I wanted my students to emerge from the class thinking more scientifically, and having a grasp of the content that defined a particular course that I was teaching. So this is just really, really important. And hopefully it's something that you're learning more about in this class. So I'm going to scroll through this and get to another note I wanted to say about science, and that was Objective 1.5, which asks you to identify and describe the common steps in the scientific method. And I provide a diagram for you that is a really great, by the way, in my opinion, a really great graphic representation of what the scientific method is. And I hope one of the things that you observed in this model is the role that observations make in the scientific method, because making observations underlines the entire method. And the scientific method could apply to experimental approaches to trying to determine whether or not a particular hypothesis is supported by some variable, but it can be laboratory oriented, but it can also be very practice oriented, because you can apply the scientific method to your own practice in your own classroom with your own students in order to try and determine methods and approaches that work best for you and your students. And it all begins with making good observations and trying to organize them in a way that helps you recognize patterns and approaches. And some of your problems could be, like, for example, if for newer teachers, there are a lot of problems associated with classroom management and class and student behavior. So you might have a problem that is associated with what can I do for this class to help manage student behavior in a more effective way. And for me, this was a huge problem I observed about my own teaching in the first couple of years. And reading more about it, watching other teachers, making more observations that way, and identifying approaches. I happen to identify some classroom management approaches that I wanted to test out, and I did, and I made observations about them, and I tested them in controlled ways, and I found things that really worked for me. I mean, absolutely. And I along with just the general experience that I had as a teacher, I also solved a lot of classroom management problems by taking a scientific approach in the first couple of years of my practice. So I just wanted to sort of underscore how important the scientific method is and how important observations are in the scientific method. That's so important, which is why teaching students how to be observant and differentiating between observations and inferences is so important. So that was something I really wanted to talk about. I also wanted to talk about, let me go back to this objective, which is define theory and differentiate a theory from a model. And then I wanted to talk about the model that I use, a diagram that I use to help differentiate between theories and models a little bit, because you'll notice that in this model that I present, I have learning theories at the top and human development theories at the top, and those are two theoretical areas that are used to inform theories of instruction, and it is theories of instruction that are used to inform models, the use of models. And then I present one example of a model to you. So I wanted to come back to this diagram and kind of just elaborate on this a little bit more with an example that goes back to what I talked about earlier regarding classroom management. So when I was doing some research on classroom management, one of the models that really struck me was a model of classroom management called collaborative learning. And it encouraged the use of groups, teaching students how to function in groups, and using that as the foundation for managing a class, and also for encouraging the learning of some really important skills related to working together. So one thing I learned about this particular model is that part of it was grounded in a theory called role theory. And role theory, just to summarize it, role theory was about how in organized groups of people, like an organized society, when people in society are given a role, or it's assumed that they should assume a role, like that's like you become a parent, and so if you're a typical commonly a female, you might take on the role. You will automatically take on the role of a mother, whatever, however that's defined in your mind. But that people do that naturally as just being shaped and formed by the society that they're from. So it's role theory. So I adopted for my own, I tested out and adopted a model of classroom management called collaborative learning. And in part of that, it was foundational to give students roles in their groups. So their group was like a micro society, and giving them roles to play, and most importantly, teaching them how to carry out those roles were fundamental to making that model work. And I can tell you, for me, I transformed the behavior of a number of students who were really management nightmares for me. And by giving them specific roles and teaching them how to carry them out in the group, I ended up being able to really manage their behavior in a lot of really important ways that just transformed my teaching. So that was an example of a model that came in part from a number of theories, and that's what I did with collaborative learning. And then the methods that I used were, again, based on the models of collaborative learning. So this may look like an abstract model, but I can assure you it's something that is used a lot in the practice of educators who thinks more scientifically about their practice. Okay, I wanted to elaborate on this Objective 1.7, identify and describe the attributes of a good theory, because I didn't really go over this a lot. But one of the most important attributes of a good theory is that it has to be falsifiable. And what we mean by that is that it has to be able to be proven wrong, a good theory. And that's a scientific theory, okay? So if you're thinking scientifically. And I wanted to elaborate with something that I see a lot in our society right now, particularly as we enter into a year of or for the next 6 months anyway, of campaigning, political campaigning, is that if you are somebody who is operating on a theory, your theory or your worldview is that your opponent, if you see things in a dichotomous way where you have an opponent, if you operate under the assumption that everything your opponent says is going to be a lie, everything, and you don't care that your opponent may have data to support what they're saying, observations, what they're saying, then you can never be proven wrong, because somebody can come to you and say, yeah, but that's not true. And then if you continually say, oh, well, you're lying, that's fake news, or whatever phrase you want to use to just discount what somebody is saying without considering the foundation for why they're saying it, then that's a very non-scientific way of thinking. And I think I used in a previous video the idea of religion is one of those, is a theory, is a non-scientific, it's founded on non-scientific kind of modeling. It doesn't mean it's not true. It just means that it's very hard to falsify the assumptions that people might make about the truth of their religion if it always comes back to, well, it's true because I believe it's true, and that's faith, and that's again, there may be a fundamental truth there, but it's not something, because you can't falsify it. It's not science. And I say this because as a science teacher, I would have students and parents challenge some of the things that I was teaching in class, like, for example, evolutionary theories, and they would explain that they operated with a different truth, a different what they believed in, which is absolutely fine. But the reality is that's not, they were challenging a scientific theory with a non-scientific one, and that makes no that's against the rules in science, and that's it for that. So I wanted to elaborate on that a little bit. I'm going to scroll down and get to a few more notes that I have as I scroll through. Again, you're welcome to have these notes when you are taking the exam, but you really have to be comfortable understanding them, because you won't have time to use them to learn something new on the exam. Okay, in Objective 1.13, defining variables and distinguishing dependent with independent variables. And again, I just wanted to remind you that so you have three types of variables that are presented in this objective: dependent, independent, and modifier. And the most important thing to remember is that the dependent variable is the variable that depends, presumably, on the independent variable. Depends on the independent variable. So, for example, if you're trying out a new classroom management model, the model itself is my independent variable. I'm trying something new, and the dependent variable would be the behavior of my students and how I would quantify that and make observations about it. It presumably their behaviors depend on what model I'm using to help manage behavior. So if I were to describe a scenario where I was testing out collaborative learning and I was recording the number of times students exhibited constructive behavior or destructive behavior, those behaviors would be my dependent variable. Hopefully that makes sense to you. And then one of the most important objectives for part one is to be able to define operational definition and identify examples of operationally defined constructs. And so I really wanted to elaborate on this, because where this is most used in a teacher's practice is in the area of trying to write good objectives, good learning objectives. And if you have good objectives and they're clear, then you'll be able to define the best approaches for helping students learn them. So they're really important. But a lot of objectives don't operationalize the skills to be learned in a way that makes them observable. And so, for example, in the Virginia Standards of Learning, the phrase "investigate and understand" is used at the beginning of almost every learning objective for science, and those words would need to be operationalized if you were going to use them as objectives. For example, well, first of all, investigate is a instructional approach, so it's not even part of an objective necessarily. It's what you want students to do in order to learn something. But what do you want them to learn? You want them to understand. Well, how do you know they understand something? How can you tell how much understanding they have, and how can you tell when they understand something? So those are the two questions that you ask yourself to operationalize something. How do you know you have understanding, and how much understanding do you have? And if you can find a way to word an objective so that you can answer those two questions with the statement, then you've operationalized it. So I wanted to, and I gave you some examples in the notes, but that's really an important thing for teachers. Okay, so I am going to scroll then now and go into part 2. And I don't have so much to say past part 1 because that's where a lot of the more abstract types of things are presented. Then we get into just a lot of really important content related to research. And I did want to stop on objective 2.1.3 and say that you need to distinguish between definitions and examples of internal and external validity. And what I wanted to say about this is that it's related to validity when you talk about the validity of an assessment. That is, does an assessment actually measure what you want it to measure? But in research, validity goes further. So internal validity addresses your ability to say that that something that you observed or something that you did, some intervention, actually caused the dependent variable to change the way you observed it. And that's internal validity. And external validity is how applicable are your observations and your findings in a piece of research, how applicable are they to other populations besides like just your classroom? And that is just such an important, these are two important concepts because there's always a tension between internal and external validity. If I tested out a classroom management approach in my class and I wanted to know whether it worked, and I versus just me becoming a better teacher, I would have to have like 2 environments where I tested out the classroom management model I wanted to test with one group of students, and I'd have to compare it to me not using it in another class with another group of students, and those 2 students would have to be equivalent. And the only way to do that is to randomly assign students to those classes. Which is very tricky to do. But if I did that, then I might have high internal validity if it turns out that my method that I was using, I had better results with it. But that's, first of all, think about all the variables that if I wanted to say then this is a better method for you, that may or may not be true. I may not be able to generalize it outside of my tightly controlled environment because most teachers can't randomly assign. Also, my students came from the populations that served my school, and it could be very different in different types of schools, in different locations of schools. So the more I control variables and have high internal validity, the less likely I'm probably going to be able to apply those results to other classes outside of my little circle. So there's always a tension there between that, and that's an important thing to consider. Okay, talked about errors there. Hopefully you understood that. Just to follow up on what I just talked about, for 2.1.6, explain common ways to improve external validity. The best way to do that is to randomly select members of the target population. So if I was doing a study to test the effectiveness of classroom management strategies for middle school students, if my interest was to create a universal model that would be applicable to any classroom in English-speaking countries, then I would need to randomly select subjects for my study that came from that large population, and not just the people who feed into my school. So, but that's the best way to improve the external validity of a study. So we have that, and I'm going to keep going. And speaking of sampling and assignments to experimental groups, on 2.2.4, you're asked to identify or classify different types of positivist research models, and the key to an experimental model is that there's random assignment. If it's not random assignment of subjects to different groups, now that doesn't mean you have to randomly select students or subjects from the larger population that you want to generalize to, but if you have experimental group, or if you have groups, test groups that you're comparing, the only way it can be an experiment is if the subjects are randomly assigned to those groups. If they're not, which is very common in education, if they're not, then it would be called something else, like quasi-experimental, or some other type of design. So that's really an important thing to consider. So when we get to part 3, one of the things I wanted to elaborate on here is that one of the things you have to do for part 3 is to be able to identify and describe characteristics of these different interpretive research models. And these are very different from positivist models. And I wanted to talk, though, a little bit about one of the probably the biggest challenge, and maybe even the biggest threat to the validity of a interpretivist study is the importance of the writing of it from the researcher. So, for example, in narrative research, one of the things that narrative research does is it's storytelling, and the researcher will observe somebody or something, some phenomenon, people, groups, or whatever, and then they'll tell that story. Newspaper reporters do this all the time, when they go in depth with trying to get to the bottom of a story, and they'll interview people and they'll write it up. And if the researchers have observed for themselves that there's something really important going on, something maybe transformative, or some really important sort of almost intangible thing that they are able to observe, their job as a researcher in that case is to write about it in a way that clearly communicates the experience and the story for you. And that all of the onus is almost entirely on the researcher's ability to write, because it's not just a matter of presenting transcripts to people. You have to write the story, and you have to tell the story. And so your voice as a writer is always going to come out in that. And so that is obviously becomes a threat to the validity of the truth of that writing. But it also underlies the most important skill you need to be a good researcher at that level, is to be a good storyteller, to be a good writer, to be able to communicate that way. And so that is, and not everybody has that skill. So, and some are better than others. So I wanted to elaborate a little bit about that in part 3. Then for part 3.2, I wanted to communicate the fact that the reason why you're doing this is because why you need to categorize response formats, like if you're doing surveys, is that the only reason why is because you the type of data you collect from a survey or something like that, the type of data you collect will inform the type of analysis you need to do when you analyze the data. And that's why I included this. It's just really important when you're reading research, when you're reading the results of surveys, to be able to better understand that the type of scale used and the data collected is going to inform what statistics you need to use. And I talk about that later on in the notes. So part 4 of the notes addresses sampling, validity, reliability, data analysis, and statistics. And I don't really get into too much of the data analysis and statistics part, because that's like a whole class in and of itself. But there was one thing that stuck out to me that I wanted to talk a little bit about, has to do with something for objective 4.2.2. Is that you should be able to determine the type of reliability measure
that is presented when in a research study or a report of some in some way. And I wanted to talk a little bit about this thing called internal consistency reliability. And the reason why I highlighted it is just because this is a statistical test that is conducted on a lot of assessment data or a lot of test data. And in fact, when I give this test in D2L to you, I'll get the data back, and it will run an analysis that gives the reliability of individual assessment items. And it's based on the fact that if you do well on one item, you should do well on another on the test, and vice versa. If you don't do well on the test as a whole, the chances of you not doing well on individual related items would also be pretty high. And so just by human nature, the fact that if you people who do well on one tend to do well on others, if it's a well-designed test, that is. And if not, if there are problems with that, then the statistics usually flag things. And so I just wanted to point that out to you, that D2L and all testing software includes statistics for internal consistency. And then for objective 4.3.1, that word parameter can be a little bit abstract, and I just wanted to say that so it's a characteristic of an entire population, whereas a statistic is a characteristic of a sample. And some common parameters that you're probably familiar with would be like the Virginia SOL scores that are reported at the state level, because what's reported are the results from all the students in Virginia who took the test, all of them. It's not a sample. They don't say that they don't base like the average SOL score for fourth grade off of just a sampling of fourth graders. They base it off of the entire Virginia population of fourth graders. Same with SAT scores. When they report the data on SAT scores, they can report all the people who take the SAT scores, all of them. So that whole population, it's not just a sample of students. And again, I mentioned earlier something about us heading into the political season, and statistics about, for example, political party affiliation can be parameters, because if you take the number of registered voters for one particular political party, that's not just a sample number. That represents all of the people registered in the whole country. About that. Although you have to know that there will be a lot of statistics that will be communicated during the election cycle, because they take polls and they give surveys out, and they only need they don't need a parameter there. They only need 1,000 survey responses in order to have a pretty high reliability that their results reflect a parameter. If, and this is a big if the subjects are randomly selected. That is so important. And finally, I'm going to end my elaboration of notes on 4.3.4, just describing correlation coefficient and the significance level, the p-value. P-value is just the probability value that if you observe something, the probability that it is what you observe and not what you think you're observing and not something else. If you observe a difference between scores between two groups, there's always a chance that any differences is due to chance. But statistically, you can analyze data and you can determine at what level of this kind of a surety do we have that any differences I observe between data sets are not just due to chance. And that's what the p-value is. It's the probability. And there are magical probabilities for different reasons. And one of them is 0.05, that's 5%, or 0.01, and that's 1%. And what those mean is that if you have a difference between sets of scores and you believe that you observed a difference, scientists generally have a cutoff. Is that difference due to chance? If there's greater than a 5% chance that it could be due to chance, then we don't call that difference significant, no matter how big it might look to you. Some scientists set the level at 1%. So, in other words, the differences between sets of scores have to be, there has to be only a 1% chance that it could be due to chance. So, otherwise, or less. Otherwise, the difference is not reported as significant. That's a pretty high bar to ask of yourself. And you might be asking, well, what are the statistics like? How do you calculate that? And how in the world could you calculate such a thing? And that is a story that is for another day, because and another class, because statistics and the math behind it is very scientific, but it's also very complex, and we don't have to address that in this class. So I just wanted to elaborate a little bit on the notes, and hopefully as you watched this, you could sort of see me and maybe see yourself going through the notes one more time and identifying some of these key ideas that I brought up, and hopefully that provides a little bit more context for you as you prepare for the upcoming midterm. So good luck, and I hope you perform well on that rather big test.